Thanks to our partners from Lyle Technologies, SignOff Semiconductors, Bharat Semiconductor Society, and Tessolve, we have a power-packed agenda. This event features key speakers from various domains of semiconductor technology who will discuss important aspects of open-source chip design and verification. We start our technical session with an exciting topic on SystemVerilog constraints and how linting can benefit users. The title of this talk is SystemVerilog Testbench Constraints Can Blind You. Build Your Guards. The speaker is Mr. Nambi, Chief Technical Officer at Lyle Technologies. Nambi will discuss the challenges of managing SystemVerilog testbench constraints and the importance of building effective guards to prevent issues in verification. His session will focus on how such constraints can obscure problems in the testbench and how open-source tools can help address these issues in more efficient ways. With real-life case studies, he will highlight the benefits of linting your constraints code using open-source PySlint-based solutions.
Hi everyone, thank you for joining. I'm Nambi from Lyle Technologies. We are a VerifWorks and Aspico partner for many years. We collaborate in open source chip design and verification innovation with VerifWorks and Aspico. So our agenda will be a quick intro about what we do at Lyle, then what are test bench constraints, and what are the challenges. Okay. So Lyle, we have extensive design verification expertise with complex SOCs and IPs. We architect, design, and implement design verification environments and audit design verification environments. So what are SV test bench constraints? These are the basic control for constraint random verification. So constraint random verification is a way to automatically generate test cases when you have a huge design or a huge IP. Okay. So what it does is it enables you to generate a range of tests, and user does not need to write all possible cases. So if it is different use cases or different capabilities that you want to check for the design, the user does not, or the DB engineer does not need to write all of these explicitly. Okay. So the constraints essentially give control for test generation, and these are like constraints at the top level. So you don't need to go inside the design and provide switches or knobs to control the generation of the test. Okay. How is it very useful? It will enable you to quickly generate corner cases. You can control what kind of tests you want to generate with providing weights. Okay. And you can also provide either static or dynamic constraints, which will enable you to generate a set of tests which are constrained statically, or you can dynamically change the constraint based on what was generated. Okay. So you can define a range of values for signals, buses, registers. Okay. And you can also define specific conditions for the system. So you can say when a system comes out of reset, for example, right, you can set a specific value to the register. And then after it comes out of reset, after a certain period of time, you can set a different random value. Okay. So based on this, different types of generation or setting constraints, the user can generate different use case scenarios for the environment or for the system that you are verifying. Okay. So there are, though the system Verilog constraints enable you to do a lot of things on the design environment or verification environment, there are challenges in managing the SV constraints. Okay. Some of the challenges I've listed here, they're not always very straightforward to manage because uh, the person who is writing the constraints or defining the constraints may not understand the system use cases, or there may not be enough knowledge about the design which is being constrained. So because of these two conditions, there are possible constraint failures that may come. One is over constraining your design or your environment. So over constraining is basically a condition where you put too much constraints on your test generation. So you don't essentially generate enough uh, tests, or you don't even generate sometimes tests at all. Okay. Under constraining is you don't have uh, any constraints, or you have very loose constraints. So in that case, what may happen is the tests that are being generated may not be meaningful tests for the system under verification. Or you may have constraint conflicts where in one place you have defined a constraint and you have a similar, or you have another constraint which is actually violating what the previous constraint was. Okay, so when you're actually using or defining SystemVerilog constraints, or constraints for that matter, it is always good to have a good understanding of the system use cases and some knowledge of the design itself. So not only is managing the constraints a challenge, debugging the constraints is also a big challenge, because when you have a huge design or a huge IP and you have a whole lot of constraints, then if you see failures in the constraint or improper generation of the test, then what is going to happen is you will not be able to debug these constraints. Okay. So how do we, hold on, please. So how do we overcome, or how do we quickly enable debug or fix of these issues with the constraints? So linting tools or some simulators enable you to highlight issues with the constraints, or they may highlight and tell you, okay, there is a possible uh, misuse of the constraint, which will enable you to, or disable you to generate good tests. Okay. Also, there are some constraint checking tools which will essentially run through your constraints and tell you if the constraints are valid or not. Okay. So I'm listing some of the open source tools that would enable you to do this. So PySlint is a solution from Verifigs as we go, which will enable you to do constraint analysis and linting. There is also VeriLaterLint, which is open source tool. There are other open source tools which will enable you to do constraint validation or constraint linting. Uh, in the use cases that I'm going to present further are based on PySlint's linting capabilities. Okay. So this, I'm going to present like 4 use cases or case studies that we have done. So the first one is the definition of weights with the dist keyword. There are 2 ways to do it, with colon equal to or colon hash. The use case is different for both of these cases. Okay, you need to have you need to understand carefully what the difference is and use the appropriate one. Okay. Because if you use the wrong one, then you're going to have difficulty finding what was the issue. So for example, we are using a distribution here where it says 0 to 31 with colon equal to 1, and this is colon equal to 1. Okay, so the caption or the description on the right hand side is actually a snippet from the IEEE SystemVerilog standard, which highlights the difference between the colon equal to operator and the colon hash colon slash operator. So in this case, when you use the colon equal to, basically you're saying the distribution is equal uh, between these two. Okay. From 100 to 101 and 103, you give equal weights. Okay. But in the case of the second case, the operator is applied to a range. So the weight is for the entire range and not for the individual elements of this array. Okay. So if you see in the previous one, you're saying you're giving a weight of 100 to, weight of 1 to 100, 101 and 102. But in the second case, you are going to say, I'm going to give a weight or the total weight divided by the number of elements in the array. So the distribution is across the array and not for individual elements of the array. Okay. So when you have a distribution definition like this, PySlint essentially gives you a violation. So you can see that this is a output from PySlint. So we have a rule defined here which says potentially incorrect constraint expression. So it is asking you to see if you actually wanted to use colon equal to or colon slash based on your requirement. Okay. So it will give you this violation so you can make an analyzed decision on what you want to do. So the second case study is using array reduction methods for constraint definition. So in this case, if you don't use a proper cast on the value, then you may end up with the improper constraint value. So for example, if you define a definition like this, where you have num list, which is an array, and you say num list colon sum equal to 1, right? In this case, what will happen is since you don't have a cast of type, okay, as int or something, right? It is going to just give you a value of 1, and it's going to be an improper comparison. While when you typecast it, the result is forced to a 32-bit value. So you actually get a proper constraint reduction constraint. Okay. Array reduction on the constraint. So PySlint has a rule to actually flag improper definition of the constraint without casting. So or typecasting on the value. So you can see that there is a PySlint violation which says missing cast. Okay. So the third case study we look at is the operator precedence on the constraints. If you don't take care about the ordering of the operators, then your constraint may be invalid or improper. So for example, we are taking this constraint. So we are saying foo select, which is a random, which is a bit, right? And we are assigning based on a conditional operator. Now, this operator is higher in precedence when compared to the conditional operator. So what may end up on foo could be a random value compared to the conditional operator. Okay. So Again, you should use proper brackets like this, so the precedence is taken care of. PySlint highlights a violation. It says improper constraint expression. So please review the use of brackets so you have the proper validation of the expression. The fourth use case is using of soft constraint versus hard constraints. Soft constraints are discarded when there is a hard constraint for the same variable. So for example, you have a soft constraint here where you say bar is equal to FF, and then you have another soft constraint where you set this bit to be always 1. But then you have a hard constraint here where you say bar is always 0. So what would happen is this soft constraint will be overridden by this constraint on bar. So what will happen is you'll have the higher order bit to be, sorry, lower order bit to be 0 always. So you'll always keep generating FE instead of FF. Okay. So you need to take care of conditions like this. And PySlint also has a violation for this, which will be highlighting that you're having a mismatch on the constraint between the soft and the hard constraints. Now, you can also add your specific rules into PySlint, so you can enable it to do better generation. Sorry, better control on the constraints. Okay. Any questions? We will, as Hema said, we will